Swayam Prabha. Digital India. Educated India.
Welcome back. So, today I want to take up the topic of speed control of induction motors. Specifically, I want to focus on starting of induction motor. So, this is one important topic that I want to take, really not so much on speed control, maybe if I time permits I will develop that theme a bit further, but main I will give some introduction also to, I mean after our starting is also speed control of the induction motor. So, if you recall, just to, sometimes it is not a recall just for you, but it is for me also. We have this, if you remember, as the equivalent circuit. This is the Thevenin's equivalent, this is the R2 by S, and this is the X2 dash, and this equivalent circuit was used to derive, the current is, this is let us say A phase, similarly you can have 3 phases. So, the current in the A phase will be I will be R Thevenin plus R2 by S plus J times of R Thevenin, I am sorry, plus J times X Thevenin plus X2 dash. This is the current in the A phase of the, in this case the current in the A phase of the induction machine, and then the power which is transferred to the secondary. That means to the secondary means what we mean is through the air gap, is basically it is the power which is transferred here to the R2 dash. This is what we, when this is what represents the secondary circuit in the equivalent circuit, and please recall this is not R2 dash, but R2 dash by S, where S is the slip of the machine, which is the synchronous speed minus the mechanical speed divided by the synchronous speed. So, suppose you have a 2-pole machine 50 hertz, then its RPM is 3000 synchronous. Suppose it is running at 2950 RPM, then its slip is just this simple small number. But if you had 4-pole machine, then the synchronous speed is 1500 RPM, and suppose it is actually running at 1400 RPM, then the slip is this. Usually I restrict my discussion to 2-pole machines, and the formulas automatically scale up. We have discussed that I think earlier, to multiple pole machines. So, this is the slip. So, the actual resistance is what? Actual resistance is only R2, but in the equivalent circuit, the resistance is shown as R2 dash by S, and if you remember, actually this came from SE2 divided by R2 dash. This is the current which is associated with I2 dash, but when you this will when it will be transferred, it will be transferred as this to the it will be transferred as this to the stator side, and it will be not at slip frequency, but at power frequency which is 50 hertz or 60 hertz. But in the actual rotor it is still at slip frequency. So, that is why if you recall, I had explained to you that induction machine is called a generalized transformer. The secondary winding here has a freedom to rotate. In a normal transformer, the secondary winding does not have a freedom to rotate. Because it has the freedom to rotate, it creates its frequency in the rotor currents are different from the frequency of the stator currents, which are of course tied to the frequency of the supply, and frequency of the rotor currents plus the frequency associated with the rotation should, multiplied by the number of pole pairs, should finally translate to the what is seen on the primary side, which is our 50 hertz or 60 hertz supply frequency. And actually this is R1, if this is the leakage resistance of the VA, and if this is the RM and say JXM, and then if this is R2 dash by S and this is JX2 dash, then this is the actual, so to say, whatever actual means, because I am saying actual and equivalent in one go, that is why I said equivalent circuit. Equivalent circuit of this, and we had done we had said okay, this are, let us treat this as the load terminal. Then we measure the open circuit voltage here, we call it as V Thevenin, which is basically this whole series, calculate this series impedance and then proportionate to this find out that voltage, and that we called it as the V Thevenin, which V Thevenin voltage here. And then we said that okay, when I am taking this terminal here to find the Thevenin's impedance, short this out. So, this branch in parallel with this branch, whatever is the equivalent impedance, that comes out as R Thevenin and JX Thevenin here, JX Thevenin here, and then now Thevenin's equivalent is this much part and the load part is this much part. The advantage of, what was the advantage of this Thevenin's representation? This is induction machine is one very good example of application of Thevenin's theorem. Usually if you just want to solve given one set of load and one this thing, you can just do a direct brute force way of solving it, but you are asked sometimes in an exam or whatever to solve it using Thevenin's equivalent, just to make sure that you have understood the tool called Thevenin's equivalent or Norton's equivalent. But it is one very good example is in the induction machine, where what you find is that the slip will be at starting will be 1, because omega s minus omega m by omega s will be omega s minus 0 by omega s, which is 1, and at synchronous speed the slip is 0. This is the slip at the synchronous speed. So, as the induction machine goes from no load starting to no load operation, the slip variation is from 1 to 0, and since this comes in the denominator, so like if the slip is 0.1, R2 dash by S will be 10 times of R2 dash, which is significantly higher resistance than at near the no load than or at full load if the slip is 0.1, then the resistance part is significantly higher than at the time of starting, which is R 2 dash, and that is why the current which is flowing through this loop, the current which is flowing through this loop reduces significantly from what current you would see at the starting. So, starting current in the induction motor is going to be high because the slip is 1, and so and then the current would reduce as you reach, would be current at full load will be lower than the current at the starting, because the slip is much more closer to 0 exactly at no load. If the slip was 0, then of course, this becomes like a open circuit here, and if it becomes like a open circuit, then what it means is resistance is infinite, it looks like a open circuit thing, and the current drawn would be 0. But actually current will never be 0, because there will be friction and windage losses which are associated with the winding. So, as the slip keeps varying in its journey from 1 to 0, every circuit if you had to solve directly, it would have been so inconvenient, but thanks to the Thevenin's and the wonderful theorem called Thevenin's equivalent, what we have got here now is that we for every slip we have this simple expression, you can put it in your MATLAB program or whatever and calculate the current, and then using this we had derived the torque expression as 3 Va square by, or rather V Thevenin square by omega s. V Thevenin is of course R 2 dash by S divided by R Thevenin plus R 2 dash by S whole square plus X Thevenin plus the leakage reactance X 2 dash whole square. Let me just check if I have 3, yeah, there is a factor of 3, that is for 3 phase, and V Thevenin square by omega s R 2 dash by this, and yeah, R equivalent is there, and R equivalent is this term, and X equivalent is this term. This is in Newton meter. And then we had also done something about maximum torque T max. We had also worked out the maximum torque T max, which will happen at some slip called S max, and for that we had set the taken the torque expression and taken its derivative and set it to 0, because at the maximum value the derivative with the slip should be 0, and then found out that and checked the second order condition that or at least I had mentioned it, if I am not sure if I had checked it formally, that the second derivative should be negative. Second derivative means, which is the second derivative I am talking of? I am talking of d square T torque divided by ds square. This should be less than 0 and this should be 0. These are the conditions for local maxima, and actually when we plot any, we can even analytically also argue that so if we plot the torque speed characteristic would look something like speed, this is your synchronous speed, slip 0, starting speed is 0, slip is 1, and this is your torque speed characteristic. This is the T max value, this is where the S max you get, and that T max S max happens at R 2 dash divided by R Thevenin square root of R Thevenin square plus x Thevenin plus R x 2 dash of square. So, this is completely determined by the parameters of induction machine, right. This is completely determined by the parameter of where at what slip the maximum torque will be obtained. So, it could be like 0.8 for example, just. So, 80% of the rated speed you will get the maximum torque, but you would be usually running it at, so say S max is 0.8, then usually no load slip will be 0.8 times range would be like 0.8 times 0.5 to 0.8 times 1 by 3 1/3, so 0.333. So, the rated operation in that the slip would be something like 0.04, and this would be like, so 0.9 by 3 if you take 0.9 by 3 is 0.3 and then divided by 10. So, like in a very small interval here from the slip varying from 0.03 to 0.04 somewhere here, let us say, this is where the rated operation would, rated torque would be. This is the maximum torque, and because this number gets fixed once the parameters are fixed. So, the maximum torque which we had also derived, T max which comes out, that number also gets fixed 3 by 2 V magnitude of Thevenin square by omega s 1 divided by R Thevenin plus square root of R Thevenin square plus this. So, very carefully you can observe that this finally has the unit of ohms, this is also unit of ohms. So, the two quantities that are getting added here are also having unit of ohms, and then V square, V Thevenin square divided by this ohms would give you basically the V square by R kind of, that gives you the unit of watts, but then you are dividing it by the speed. So, that gives you the unit of torque. I mean, I mention all these things because there are so many ways in which we can err, silly mistakes and things like that. Every time it is not possible for us to open a book or a manual or something and check. So, our mind should be continuously looking for a feedback that whether I am doing things rightly or I am not doing things rightly, and if I am not doing things rightly, how do I take care of it. So, dimensionality check is one way of looking at it. Okay. So, therefore, the torque becomes constant. Now, imagine that I do something, I create a circuit like this. I have a supply. So, this is my 3-phase supply. I have the switches here, basically a circuit breaker, 3-phase circuit breaker in one go all the 3 switches will be closed. I won't be closing it one at a time. So, I have something like this, and this indicates, usually all circuits should have switches, right. Many times we do not show it, but please be sure, please understand that. Have you seen any real life circuit in your home or anywhere else which does not have a switch? So, you should, whenever you are doing formal work, you should make a habit to show the switch in the circuit which will be closed or opened, and a circuit could have multiple number of switches, like this being a 3-phase circuit has three switches. And then I have this 3-phase stator winding connecting here. So, the 3-phase stator winding connecting here, and I have a 3-phase rotor winding. This is just drawn neatly. I mean, I am not taking care of any other thing, really speaking. Do not try to read too much into which is A phase, B phase, C phase and all that. I am basically trying to do a neat drawing, because that discussion is not right now very relevant to me. And so these are the 3 phases which are there, and then you can think of these being connected to some kind of brushes. Let me change the color now. You can think of these being connected to some kind of brushes, maybe good way could be this itself. This is one brush, this is another brush, this is the third brush. Not really brush, actually I wanted to draw slip ring. So, they get connected to a slip ring like this. Oops. 3 rings basically. Sorry, today the figures are taking some more time than what I usually take. Duplicate, and then actually the rings need not be circular, but I just did this way. And then there is a brush contact here. Maybe I should use slightly different color for the brush contact. So, I have a brush contact here, I have a brush contact here, I have a brush contact here, and now what I have got here is that so this one here is connected somewhere to this one, and then this one is connected to this brush, and this brush is connected to this brush. And then from these 3 brushes and these contacts, slip rings and the brushes, these are my slip rings and these are my brushes. So, it is a ring like this, copper or something, on which carbon or some kind of thing brush sits on it, and when there is a rotation, the slip ring rotates, but the brush holds the contact. So, there is obviously going to be wear and tear when the brush rotates. But I mean, if you go for what I am discussing right now, that is going to happen. You do not have really a choice. And then what I have here now is, so let me to make space for this, let me call these are my slip rings, and think of a kind of a circle here, and a resistor like this, a resistor like this, and a resistor like this, and I have a arm here which is called as the off arm, and then there is the third lever which is sitting here, and so when I I want to start connect this, I move it in this direction. So, this contact comes and touches here, this contact comes and touches here, this contact comes and touches here. So, what I do is to close the circuit, I connect this to this, okay, and I connect this to this, and I connect the second one. This is a better way of connecting it. I connect this to this. So, these are my 3 levers. These are my 3 levers, and I do this when I switch on. So, this is supply side, this is the stator winding, this is, so this is here, this discussion whatever I am doing right now, this is only valid with respect to the slip ring motor, slip ring induction motor, and in a slip ring induction motor, stator winding, rotor winding, the rotor winding, the one set of contacts is here in the star connection, other sets are made available outside, and then they have been brought out to some kind of slip rings, and on that with carbon brushes, this side is sitting outside, you know, is like somewhere keeping the box here, something like that. This is on the shaft. So, these slip rings rotate because of their being on the shaft. The brush contacts bring it to the stationary objects outside, and then here I have a very starting resistance as it is called. This is, I will come to that why I need a starting resistance. It's very quickly I will come to that. So but now what I am doing is I am not short circuiting it. I want to get some control on the torque speed characteristic. Leakage inductances in this expression, this cannot be controlled, this cannot be controlled, X Thevenin cannot be controlled, this cannot be controlled, these things cannot be controlled. So, really speaking, what I can control, slip will be determined, I am not controlling the slip. What I can only control really speaking is R2 dash, and how I am controlling the R2 dash? By connecting 3 resistors in series before closing this. So, when I will move this to here, this contact to here, when this contact for example comes here and this contact comes here and this contact comes here, then it is like this winding, getting connected to set of 3 equal resistances like this, and like this, and then getting connected. from these resistances are the external resistances equal in value, because we want to make a balanced circuit. So, what happens with the rotor winding, instead of having just R 2 dash by S, now what we have is R 2 dash plus R exterior by S, because this resistance here, this resistance here is directly adding to, I could have added an inductor also, but that is not usually done, because the torque is proportional to R 2 dash by S. So, I really do not want to, I really do not get such a good handle by connecting a inductor there. I could have equivalently got a control on x 2 dash, and that also has an indirect control on the mechanical torque. But if you look at it, actually the torque equation is says that torque is directly proportional to R 2 dash by S. So, if I could alter R 2 dash, I could alter this equation very quickly for any given slip. So, what I am trying to do here is, this is being R 2 dash plus R external by S, this will get replaced by the same value, and I will get a new torque equation in which I have some control on this I have some control on the torque by changing the resistance, and of course, slip will also adjust, because the load also has a torque speed characteristic. So, if the load, for example, if the load has a torque speed characteristic like this, then this is where it is operating. Now, if I change this characteristic to something like this by altering the resistance of the in the rotor circuit, then to develop the same torque, the slip will change to this value. So, the power output is of course altered, and and this is also altered. So, yes, if I know this much torque I want, but I am willing to have some range of speed in which, then if I alter this, I can alter these values. You roughly get the feel, I guess, of what I am trying to say. So, what I am trying to say is, I can get a control on the torque speed characteristic by connecting, one way is connecting in series external resistances in the rotor circuit. Now, how will the torque speed characteristic alter? So, let us take this figure, basic figure that we had. Let me take this figure down below. Now, look at this, what was my expression for the maximum torque? This is critical, please look at this very carefully. The maximum torque depends upon V Thevenin square, R Thevenin square, and x Thevenin plus x 2 dash square. Is any of this value, does any of this value depend upon the external resistance which I am adding in the rotor circuit? When I did the Thevenin's equivalent, I said this is the load side. So, now this side I am changing to R external by S and so on, but anything on this side is not altered. If anything on this side is not altered, is the Thevenin's equivalent altered in any sense? Thevenin's equivalent is not altered in any way. So, because the Thevenin's equivalent is not altered on any way, you see that this V Thevenin is not going to change, R Thevenin is not changing, X Thevenin is not changing. X 2 dash anyway on the load side I have only added resistance, I have not altered x 2 dash. So, this is also not changed. So, is the maximum torque altered by adding the Thevenin's resistance in the, is the maximum torque altered by adding the Thevenin's resistance in the circuit? Maximum torque is not altered, maximum torque is constant, even though I can, but what is altered is the slip. This R 2 dash is now R 2 dash plus R Thevenin dash, you should actually this R2 dash R Thevenin also you should be transforming it through the A square to the primary side. So, this will be altered and then everything else in the denominator is not altered. So, as you keep on increasing the resistance here, the S max will keep increasing. So, the S max is 0 here, is 1 here. So, that means as I keep on increasing the resistance, these points will keep shifting in this direction. So, the I'll draw this side first and I'll talk of the this thing here. Now, what happens to what happens at S is equal to 1? At S is equal to 1, at S is equal to at S is equal to 1, basically R Thevenin plus R 2 dash and this comes into R 2 dash, this comes into the picture. Now, this comes on the square of this term R Thevenin plus, so R 2 dash, and this R 2 dash is altering due to the external impedance that we are adding. So, this R 2 dash plus R 2 dash square divided by x, the denominator is altering no doubt, because this is altering as I this is altering as I keep altering, starting time I am talking of, and this on the numerator R 2 dash is also again altering, but here it directly alters in proportion to the this thing, while here it is that alteration is somewhat damped due to the presence of this R Thevenin and this big term sitting here. So, therefore, the denominator will not change that significantly, but the numerator will change much more significantly. So, what it means is if I increase by adding external resistance, if I increase the net resistance in the rotor circuit, it will transform for the same slip 1, it will transform into larger value of the torque. So, the starting torque usually will be more. So, as I increase the resistance, the starting torque will be 1, and if I say that if I set this R 2 dash plus R exterior dash to be equal to under root of R Thevenin square plus x Thevenin plus x 2 dash square, if I set it to this value, then R 2 dash plus this, if I set it to this value, what will be S max? The S max will become 1. So, S max will become 1 means maximum torque will be obtained at unit slip or at the starting position. So, in that case, this figure, the extreme figure would be something like this, but the slip is still at synchronous speed, the torque will always be 0, and so this point is fixed. So, you can see that if this is the R external increasing, a very interesting torque speed characteristic is seen. We see that maximum torque is not altered by adding external resistance, but starting torque can be increased if I want. And what about starting current? The starting current will of course reduce. Why will starting current reduce? Because the starting current S is 1, and if I increase resistance somewhere here, then the denominator increases. So, the starting current will also reduce. So, I can reduce the starting current, I can increase the torque by having the R 2 dash or the external equivalent circuit in place. And understand that at starting current may be 4 to 7 times the full load current. Why? Because under normal and operating conditions slip is very small, If the slip is very small, this resistance is much larger, as I talked to you earlier. The current is less, but when you start the machine, then the slip is 1. So, slip is 1, so the rotor side presents a very small, much less impedance. So, huge current will flow into the induction machine, and if the induction machine current is 4 to 6 times, voltage drop will be there significantly, because lot of power is going to be sucked out from the lines to which are coming to your home. So, at your home terminal itself, or wherever you are, industry or wherever you are, you will see a dip in the voltage, and that dip in voltage can cause flicker in the, it can cause flicker in the light. So, it's a the voltage quality is disturbed. So, that is not a acceptable thing. So, direct start of induction motors, small motors is okay, but large motors we usually do not do direct start of the motors. So, we should control the current which is flowing at the point of starting, which is going into the machine. And if you have a slip ring induction motor, that means not a cage rotor, but 3 separate windings are available to you on the rotor side, then you could have this kind of a arrangement that I am discussing, and increase the external resistance in the circuit at the time of starting. This is exactly what will happen when I start it here. It will come here. First I will close these switches, then I will move this, close these switches. So, this whole of this resistance will come into the series. So, I will get low value of low than the normal. If these windings were just short circuited, I will get much less current than that, and a higher torque also, and my machine will start. And this is called a starter resistance, which is introduced. And then as I move this from this lever from here to here, finally what will happen, this lever will come here, this lever will come here, and the third lever will come here, and so you will get 3 levers like this, which means that these 3 resistances are completely cut off now, and the 3 windings are short circuited, and you will be able to run. You should not run a induction machine with external resistance included in it at its full load condition, because then I square R2 dash plus X Thevenin's dash, which is the loss which is happening in the rotor winding, is going to be significantly more. If the heat generated is significantly more, then the machine cannot be run for more than 2 to 3, 4 hours before it will start getting excessively heated. And if the external resistance is included, then normal operating time, the slip will also be more. If the slip is more, there will be more eddy current losses in the rotor also. So, they will also contribute more to your this thing. So, this rotor resistance has to be introduced at the time of starting and should be cut off as you move in the normal operation. And you can, if you want, you can use it for speed control also, like I want this torque at this slip, then you can alter, you could say that I want this torque at this slip, then you can figure out what is the impedance to be introduced and bring your curve to this particular curve. But then this is not the most efficient way of control, because as I said that extra resistance which is introduced creates a unnecessary losses. But for starting, this is a good effective way of starting a slip ring induction motor. Now, let us come to the case of a cage rotor. Suppose the induction machine is a cage rotor machine. Then if you just increase the cage, see, I am sorry, I made made that statement that machine will get overheated. In the slip ring machine will not get overheated, because the external resistance is outside, you could have cooling there and all that etc., but still it is a problematic thing. But suppose if you had a cage rotor, in the cage rotor what happens, basically 3 phase windings are short circuited, then they become copper bars as we had discussed earlier, stacked around, and then that is this thing. And now suppose I want to reduce the current at the start time of starting. Then what I would have to do? I would have to reduce the resistance of those bars, and those same lower value of resistance would also, sorry, higher value of the resistance would also be operational when the induction machine is running at its full load condition, thereby unnecessarily creating losses, which more losses, which reduce the efficiency of the machine, which is definitely not a good point, and also creating more heat dissipation, which will not allow us to run it for a significant period of time like 2 to 4 hours or whatever. So, in this case, and once the construction is such, the construction is such of the cage rotor, then I cannot introduce external resistance from outside. So, if I cannot introduce the external resistance from outside, then how should I control the current at the time of starting? How should I get that control? The only way to get that control is by altering the supply voltage, that is all, because now the secondary rotor side I have nothing, its bars are shorted, it is all sealed, and that is the simplicity of the cage construction, it is fireproof, everything is there, but no huge current it will draw at the time of starting. I do not want it to draw the huge current. So, what I should do? I should attenuate the input voltage, and to attenuate the input voltage, what should I do? I will introduce a I will introduce basically a auto transformer in the picture. So, I can have a starter which is basically a auto transformer, and let us say I tap it at say 50% value here, I tap it at 50% value here, and I tap it at the 50% value here, and then I have this to the 3 windings. This indicates the what is available at the outside boundary of the motor. So, it is available at the outside boundary of the motor. Now, let us say this auto transformer is rated 1:n, primary is to secondary. And what is the secondary side? The secondary side the turns ratio is 1:n. So, the primary side is this supply side, and so the voltage here is n times of phase voltage, and if the secondary side voltage current is I motor current is say I m, then this current will become n times of I m. The voltage here becomes n side, reciprocally on the primary side the current becomes n times. So, this is the way I have drawn, and my n is here say half of the value. So, I have taken n as 0.5. So, because the torque is proportional to V Thevenin square, which is approximately, let us say the torque is proportional to V A square, if I have reduced if I have reduced the if I have reduced the voltage applied by 50%, what will happen to torque? Torque will only become 0.25%. In general, if I have used a factor of n here as the turns ratio instead of 0.5, if I generalize it, that voltage is altered by 0.5, and the torque will become n square times of that. So, I will get what I can sort of say, a statement that I can make is that starting torque with auto transformer divided by starting torque with direct switching is going to be basically the output voltage of the auto transformer divided by the input voltage, which is the supply voltage, that you cannot change, square of this, which is n square. This is exactly the point that I made a statement to you just now. So, therefore, I can what I can do is I can reduce the torque at the time of starting. So, it will not feel the jerk. It will start with a low machine impedance is the machine inertia is the same. Start like you see how you start a car, first of all you start the engine, like that it is, engine is now revving up at its normal speed. Then you put the gear and then you start accelerating. So, it is like this, first start it with a low torque value, let it come close to its synchronous speed, then you can connect the load to it. And by reducing the voltage, not only we have reduced the starting torque and not connected the load, and we have also controlled the current, because voltage is so let us disclose that discussion of the current also. So, suppose I had directly say at the time of starting, when I put S is equal to 1, all this equivalent circuit here, all of this thing is written as Z naught. Then what is the initial current, that is starting current? V A by Z naught, or V phase by Z naught, if I am using phase, let us say V A. So, the starting current is direct start, the starting current is given by this particular value. But when I use a auto transformer, say n is 0.5, secondary voltage is 50% only, then what happens to the current on the motor current? It becomes n Vp by Z naught. This is on the secondary side of, which secondary side? Not of the induction motor, of secondary side of auto transformer. This becomes so much on the secondary side of the auto transformer, and then on the primary side what will happen? It will further increase by n. So, n is 0.5 means it will actually further reduce by a factor of 0.5 when you go from secondary side to the. So, here itself it has reduced by 50%. When it goes from this secondary side of the auto transformer to the primary side of the auto transformer, it will reduce by another 50%, or in actually multiply by n, but that because n is less than 1, it will actually reduce by another 50%. So, therefore, what will happen to the starting current with auto transformer? With auto transformer, this starting current, this is the starting current, okay. Without this is the starting current direct, I am sorry, this is the starting current direct start. Now, when I have the auto transformer in picture, then the starting current is going to be n square Vp by Z naught, which is nothing but which basically means that starting current with auto transformer divided by the starting current with direct switching becomes also n square. So, you can reduce the starting torque by n square and you can reduce the starting current also by n square, but it requires this auto starter, this auto transformer setup, which is a bit of a which can be a bit of a expensive proposition. So, suppose you you want a cheap solution to it. The cheap solution will not be as good as this solution that I am talking on, but suppose you want a cheap solution to it, then you could also opt for star delta starter. So, in this what we do in the star delta thing is that the two ends of the each phase of the starter windings, they are brought out to the starter, okay, which is moved from starting position, connects it in the star configuration. So all the 6 points are there. When you start the machine, these 3 stator windings are connected in the star configuration. If you connect it in the star configuration, and once the machine has started, then it is moved into delta configuration. So the supply voltage is the same. Now, if I connect the 3 windings, if I connect the 3 windings in star, supply is the same, then I will get here only 1 by root 3 of this line voltage which is here, and then when I change it to delta, so what will happen? This whole VL voltage will get applied on this. So you will have everything scaled down, So the voltage is made 1 by root 3 times. So the torque will become one third, and similar argument will show that the current will also become 1/3 at the time of starting, because the stator windings are connected in star at the time of starting, and then when they are moved to this thing, whatever you get will becomes 3 times more or less of that condition. So you can bring basically the starting current down and starting torque down by 1/3 of the value if you go for a star delta transformer by first connecting these windings in star and then moving it on to delta configuration. So you do not need a extra auto transformer. So these are some different ways of starting the induction motor, and that is it for today. We will continue in the next class. Thank you.